part, we would also like to announce some of our future meetups. So in March, Brian will give a talk about dynamic quantum circuits. And later in March, Anna Naden will give a talk about Shor's algorithm. So Anna is with us today as well. Later in April, Zeki Seskier will tell us about the landscape of the quantum startup ecosystem. And later in April, Dr. Wong will give an introduction to quantum computing from algorithms to hardware. And we would also like to thank our partners for supporting us, helping us organize this meetup. And I think that with this, I can stop sharing my slides. And Ron, if you are ready, we can start and the Zoom is yours.
Okay, thanks. Very good.
Yeah, thanks for accepting our invitation. We are looking forward to your talk.
Okay, so my screen share should be working now. I got my tools and my stop button. Perfect.
Yes.
Okay, yeah. So good afternoon. I'd like to thank everybody for coming to this session of Washington, D.C. Quantum Computing Meetup Group. I am very honored to have been invited to present to this group on the topic of quantum tool chains, both now and in the future. Last year, I attended a online conference that was hosted by a Southern California university. Sessions at this conference highlighted quantum projects around the country and around the world. During one particular session, I remember hearing a professor, possibly one from Yale, make the following statement: "We are at the vacuum tube stage with quantum hardware." And the more I thought about that phrase, the more I realized it was pretty close to the truth. The vacuum tube was at the very beginning of the electronic computing era. And from a hardware or physical device standpoint, we are clearly at the beginning of the quantum computing era. It's still interesting to note that some people consider the vacuum tube to be one of the first quantum devices, even though it wasn't exploited at the quantum mechanical level. So today, we will be taking a high-level flight over toolchain country with a look at the past, the present, and the possibilities for the future. Along the way, we will also touch on the technologies of computer languages. As you can see, our agenda starts with a brief look at history. Then we'll quickly go over current computing languages and compiler technologies that are in use today. Moving on, we'll get a snapshot of quantum computing in the here and now. This will be followed by the fun part of trying to imagine what the future will bring. To wrap up, we'll engage in an open discussion. Hopefully this will inspire some out-of-the-box brainstorming on the possibilities for the future. Who among us has heard the phrase, "They who ignore history are doomed to repeat it"? With that in mind, I will start our history tour with the first electronic computers. When they came out, there wasn't a whole lot of software to support them. The phrase "whole lot" may even be generous here. Even the term programming here might be generous, as getting one of these beasts to run a single computational job required a team of people. On the slide, you can see in the upper left corner is a picture of the ENIAC computer. I'm not sure if this is a model or if it's the actual original device. It's sitting in a glass cage at a computer museum somewhere in Pennsylvania. You'll notice it's got a lot of wires hanging out the front, a lot of what appear to be switches and jacks and knobs and plugs. Also, if you notice in the background of this slide, there's an image of what was used as a setup sheet for setting the machine up to run a job. And that's this, this thing in the background you can see on this slide. Now, this graphic isn't very legible. It's pretty low resolution, but if you step back and look at it, it kind of gives you the feeling of a quantum circuit timeline. Did we just come for a full circle? At the bottom, we see what were then called programmers. They were, for the most part, ladies who would follow the setup sheets and go into the computer cavern to set them up by throwing switches and plugging in patch cables from point A to point B to configure the machine to run a given algorithm or a job. Now we're moving on to the first microprocessors. And yes, I'm doing a pretty good leap here in the history line, going from the first electronic computer to microprocessors. In between, there were mainframe computers and the beginning of the mini and super mini computer era. The mainframes and minis started using higher level languages, things like Fortran, COBOL. C was in its infancy, but you did see it become available from companies like Digital Equipment Corp. With the introduction of the Intel 4004, which is generally considered the first microprocessor, there wasn't a lot of software support for it. It wasn't big enough to run the high-level languages found on the still room-sized industrial computers. After all, it was just a 4-bit CPU. Programming the 4004 may have started out as a tedious task of using a hex editor to sequence machine instructions. In the center of this slide is a 4004 on a 16-pin dual inline, or what was called a DIP package. In the upper left is a picture of the 4004 chip, sometimes called a die. It fit snugly under the gold cap of the DIP package. I don't know that this processor ever made it into production anywhere, although I have seen pictures of it in multiple packages types. So it's possible that Intel did make enough of them to go into production somewhere. In the lower left, we have an 8008. That's this guy right here. The 8008 was an 8-bit CPU with a 16-bit address space. But if you notice, it's only got 2 more pins than the 4004. It's in an 18-pin package. Turning the 8008 into a functional product required quite a lot of support circuitry, but the good news was that by the time it came out, assemblers and macro assemblers were available for it. There was even something called Tiny C that could generate 8008 machine instructions from a high-level language. Once again, we see hardware being released and software technology playing catch-up. Down here in the lower right, we have this picture of a colored die. I'm not sure which CPU it belongs to, but I just like the colors, so I included it in the presentation. Okay, moving on to another entry in the hardware saga, and something that I had experience with was something called the transputer. Transputers were early SoCs, or systems on a chip, and they were provided by a company called InMOS. Their flagship product at the time was the T800. In the lower right, you can see a picture of a pair of T800s mounted on a card with a new bus edge connector. This card was compatible with Apple Macintoshes that had new bus backplanes. The T800 was a very interesting product, as you could build circuits with just the chip. It didn't require really a whole lot of external circuitry. T800s had a fairly large address space and a reasonably fast CPU. And if you didn't need a lot of memory, you could basically run these chips standalone by just providing a reset circuit and possibly some sort of external clock. Although I think the T800 did have some kind of internal clock capability. As you can see on this board, the T800 is accompanied by a big chunk of external dynamic RAM in the form of single inline or SIP packages. The T800s had a dynamic RAM controller built in. This gave each T800 something like 128K or more of RAM. Probably the best T800 feature was that they each had 4 bidirectional serial data pipes that allowed you to connect T800s together, sometimes in very large arrays. If you look in the lower left, you can see, if you look in the lower left, you can see how you can configure a set of 4 T800s in a ring topology, and at that same time a crosspoint technology, and that's this circuit here or this topology map here in the lower left. Now, if you look back at the board again, we see the blue connectors and the external connectors. The blue connectors via the patch cables allowed you to connect the T800s to each other or to external connectors. The external connectors provided outbound and inbound traffic connections to what could be a very large array of transputers, as many as 10,000. Once again, software and this time algorithms lagged behind, as you could build a massively parallel machine with it at the time with a ton of computational power, but there was no software or algorithms that could keep 10,000 T800s busy. What topologies would work best, and how does the host computer keep track of it, of what's going on? So there was a lot of research into the topologies for these kind of things, these concept of having multiple computing nodes connected in trees or graphs like this. I first saw transputers at a computer trade show where InMOS was running a demo with a small nest of T800s. The demo was merging global radar elevation data with Earth satellite imagery into 3D scenes. And actually the 3D was continuous 3D scenes or 3D video. It was doing this all in real time. Input to the demo was via a joystick that allowed you to fly through the mountains of California. At the time, as a new pilot, it was the coolest thing I had seen. Today, we take this kind of thing for granted. Google Earth, anybody? Transputers spawned much research, but ultimately failed. And one of the main reasons is our next step in history. Enter the GPUs. So our last stop in history land is the GPU. The GeForce 256, which is here in the upper left, was the first GPU presented by NVIDIA. It was pretty amazing for its time, but was dedicated to graphics processing, and the chips were found on graphics cards. At the beginning of their life cycle, it was not easy to utilize the power of a GPU for things other than graphics, like, say, computationally intensive number crunching. There were people who did try things, but again, no software support for just number crunching, so work was done by hand. We take a big jump ahead in CPU land and look at NVIDIA's A100. That's this guy here in the lower left. This product is available today, and yes, we are sliding out of history country a little bit. A lot of software has changed between the 256 and the A100, like the CUDA framework. Once again, the software and the algorithms had to chase each new hardware release, and today's GPUs and CUDA framework are a cornerstone of the machine learning world. Okay, I did say we were slipping out of history, so let's take a quick look at what's coming down the line in GPU land. In 2022, I attended NVIDIA's virtual online week of technology and sat in quite a few sessions where they talked about how their main challenge was to find ways of getting the drivers and the algorithms in their frameworks to take advantage of their latest and greatest GPU, the H100, which is this guy right here. It basically came down to this new chip has so much performance and so much capability that the problem is, how do you keep it busy? Again, does this sound familiar? It feels like a lot of effort is being expended to make sure software and algorithms are not so far behind the release of hardware. One thing I'd like to mention about this slide, you'll notice the first generation of GPUs, it was just a chip. But now you can see as they moved up to the A100, they became modules. In the H100 series is a module. And there are people who are making compute modules where they have these cards that have edge connectors on them, and they can be, and they have a GPU on them, and they can be plugged into, again, massive arrays or a motherboard with a number of slots for as many GPU modules that you can fit on there. So that's something that's also changing the way of getting GPUs out into the real world beyond graphics. So, and again, you can clearly see that GPUs kind of put the stakes in the coffin for things like transputers and computationally intensive technologies that preceded it. So we'll wrap up history. Has the industry learned its lesson? Are the software and algorithms lags at least getting shorter? This time around, we're not in a software vacuum. There's a whole bunch of software, there's a whole bunch of research, there's a whole bunch of quantum understanding going on. So at this point, so that's the end of the history. I'll take a pause here if anybody wants to bring up a question.
Yeah, so there's one question on our chat from Vishal. Are there any analog circuits instead of using a GPU?
I'm sorry, can you repeat that?
Yes. Are there any analog circuits instead of using a GPU?
I'm not aware. I know there's analog computing. I'm not aware of any technology that competes with the performance of, you know, the current GPU technology. But analog, you know, this analog, classical, digital, and quantum, they all have their strengths. Maybe there's a problem analog can do better. So it's something to keep in mind.
Okay, good, thanks. I don't see more questions now. Yeah,
Okay.
there's one more. Can you discuss parallelism programming through PVM? I'm not sure what PVM stands for, so maybe Aaron, maybe you can unmute yourself and
oh yeah. And I'm not an expert at this, so
okay.
But my sort of following this like a TV show for 25 plus years is that there's been a software version of this sort of evolution too, where you know, like HPC and large scale parallel processing programming languages have been constructed mostly out of the research community in the 90s and 2000s, but now obviously it's exploded out into the large, you know, mega cloud providers and large AI and everything else in the last, you know, decade or so. I'm just wondering if you have any kind of commentary on that at all, or if that's a part of a completely different talk or completely out of bounds. I mean, whichever answer is totally fair. So
yeah, so if you can remember what some of the stuff I presented on transputers, it's kind of where we're at in the data center domain. You know, places like Google and Amazon and whoever, they have these massive arrays of nodes in under their capability. So yeah, over the years, technology has evolved to allow those things to communicate better. I mean, one thing that's better about a data center is you're not limited to point-to-point connection. You know, they've got any number of internal networks that can allow these things to talk to each other. Server communication, things like application load sharing. There's all that technology is out there to make use of like distributed an application. That same technology is out there for distributing computationally intensive problems to as many nodes that you can find in your network. Even if it's something, even if all those nodes have GPUs on them, that might be what you need to do to get your problem solved. So that is kind of a whole different area, and it's technology that's grown kind of out of this whole communication issue. So I think that's about all I can say about it at the time.
Okay, thanks, Ron. There's one more question on our chat from Sonil. It's quite long, so Sonil, maybe you can also unmute yourself and ask.
Yeah, hi, can you hear me?
Yes, we can hear you.
Yeah, so my question is that back in the 80s or even earlier, in-circuit emulators used to be a thing, and simulators weren't really there. And then simulators slowly took over, and now, you see this when developing software for, for example, the iPad. You have an iPad simulator that you can run stuff on. By the same token, we're seeing more visual programming versus high-level language programming. For example, Swift UI. Yes, it is text-based, but it's text and you see a representation of what you're doing on the side. And sorry, I'm picking Apple just because I use Apple all the time. But in quantum computing, are we seeing the same kind of shift? In other words, the new paradigm is a visual design. And the reason I'm asking that is that I took a look at some of the papers from Bob Kirky, I guess, on ZX calculus. And that seems like it's almost completely visual in nature. And it also shows how people can optimize quantum circuits. So I wanted to get your feeling on that.
Well, I'll answer in two parts. First part is, yeah, I know what an in-circuit emulator was, or ICE.
Right.
Intel's famous blue cube, or the Intel Ice Cube, was an in-circuit emulator. Now, those in-circuit emulators were hardware-based, so there was a big cable came off of the blue Ice Cube, and you plugged it into your board where your CPU would normally plug in, and the ICE gave you the ability to load programs, debug programs, and do a whole bunch of things inside of the Ice Cube box. Now, this is in a time where C was in its infancy for CPUs of that generation. So you were debugging at the assembly level most of the time. On to your other part of your question is, I'm going to defer that first, and hopefully in the upcoming sessions we'll have some talking points on that as far as what future tools or what graphical tools we have to look at.
All right. Yeah, sounds good. Thank you.
All right, I don't see more questions now, so I think we can go on.
Okay. So we're starting to the next section of my presentation. I'm going to talk a little bit about current languages and some compiler tech. So much for history. Let's move on. I feel it's very important to look at the current state of these things, given that quantum has already prompted new computing languages. As this graphic shows, we live in a sea of computer languages, and this doesn't include a vast number of libraries and frameworks. Some would say that there are just too many languages. Others might say we are in great shape. One problem with there being so many is, which one do you choose to learn? You can't really learn them all. There's also the issue of which language to use for building frameworks or a new technology. Do you need to support multiple languages for your new framework? If the framework for your new technology is written in one language, will you be able to interface it with other frameworks written in other languages? Now I'll take a quick tour of compiler infrastructure as it exists today. The main compiler suites I'm going to talk about are listed in the upper left here. GCC, LLVM, and Visual Studio. Although Visual Studio isn't really a compiler suite per se, but in its core, there is something that's akin to it. So I'm just going to concentrate on these three. Excuse me. The basic capabilities of these different suites are to be able to read in multiple different languages and to generate code for multiple different architectures, which make them very flexible and bendable. For example, GCC can read in C code. There's actually a Fortran plugin, and who knows how many other languages it can plug into. And GCC can emit code for any number of computer platforms, x86, SoCs, like the SoC that's on a Raspberry Pi, etc. The main components of a compiler suite are listed on this slide. Lexical analysis is the front end that is looking for tokens in your source code, things like numbers, string symbols, operators, etc. Tokens are then passed to a parser. The parser's job is to put those tokens together and create the abstract syntax tree, or the AST. An AST is basically a hierarchical representation of the operations that must be performed to run your code. Note a graphic representation of an AST is in the background. So that's a tree behind this envelope here. The key word in AST is abstract, which is important for the next phase, which is emitting. Emitting walks the AST and generates code for a particular hardware architecture, which takes advantage of the abstract nature of the AST. Some compilers have an optimization phase, which is used in the emitting process. This is basically where the machine code is checked and, if possible, can be modified to improve the performance of the code on a particular piece of hardware. One such technique used there was something called peephole optimization, which could change the order of the instructions to help keep the CPU busy all the time. Here we are again. Does that sound familiar? We're struggling to keep the CPU busy. Let's say you want to build your own computer language. How would you start? Well, there are some standards and tools out there that can help you get underway. You could start by defining your own language in a Backus-NAR form, BNF for short, which is a language used to define other languages. In the upper left of this slide, you can see an example of a BNF script. These are production rules. The way you read the very first line is a postal address is produced when you see a name part followed by a street address part followed by a zip part. Other lines further down in the script describe the production rules for each of the subparts. For example, the name, the address, and the zip. And actually, the very next line defines the production rules for a name part. In this way, BNF forms a hierarchy of rules. As you walk down the hierarchy, you will eventually hit a production statement made up of atomic elements, also known as tokens. Example of tokens include strings, numbers, and operators. A complete BNF definition is commonly referred to as the grammar for a parser. Once the parser definition is complete, a lexical analyzer is required to read the input text for your new language and break it up into the tokens needed by your language's parser. In a similar way that BNF can define the rules for a parser, other standards are available to define the rules for a lexical analyzer. Rules for lexical analysis are sometimes referred to as pattern statements, and indeed, lexical analysis can be done with simple regular expression matches or regexes. The lexical analyzer, sometimes just called a lexer, is the basis for the syntax of your new language. Okay, now that you have the rules for your parser and lexer, what do you do next? I'm going to fly something on here. Enter Lex and Yak. These tools were born in the Unix world. Lex is short for lexical analyzer, and Yak was an acronym for yet another compiler. Compiler was a big joke back in the day. In the open source world, these tools have become Flex and Bison. Bison not being a Yak. Lex is a general purpose lexical analyzer builder. It takes input patterns that look a little bit like BNF, just a bit simpler, and creates a C program, which is compiled into your Lexer object. When the Lexer object is called, it consumes the input text stream of the source code until it finds a valid token, which it returns to the caller. In a similar manner, Yak or Bison takes in BNF and creates a C program which is compiled into your parser object. The parser object calls the Lexer object to collect the next token and continues to do so until enough tokens are strung together to satisfy a parser production rule. Every time a parser production rule is satisfied, the parser executes the action for that rule. The action can output code immediately, or more typically will make an entry in an abstract syntax tree. Remember that from previously? If you go the route of building an AST, which is an intermediate representation of the program to be compiled, you will need to build a code emitter. The code emitter walks the AST and outputs device-specific code that will run on specific hardware. In this way, you can build multiple code emitters, one for each hardware platform that you want to support. The final step in creating your compiler is to link the Lexer object, the parser object, some initialization start instructions, and all of your code emitters into a single executable. Doing this today would most likely use the Flex and Bison open source tools, which generate C code. But there are Python libraries for Flex and Bison, I believe, that basically do the same thing, and you can build your compiler in Python. This set of tools can also be used to create transpilers, which can convert one language to another. Another common technique used for simple compiler building is the concept of recursive function branching. So we'll drop this out. Or RFB parser for short. RFB parsers tend to have their lexical analyzers built in and are good for really simple languages. A simple language does not include semi-ambiguous production rules that require lots of what is called look-ahead parsing. I've built a number of simple languages using an RFB parser, all implemented in Python. And I've been pretty content with the results. To finish up on compiler tech, I would mention that a number of concepts introduced on this slide can be complete presentations all their own. So I'll take a break here. If there are more questions.
Okay, let's maybe wait. I don't see new questions on our chat, but let's give opportunity to just maybe write some questions, or maybe someone would like to unmute and ask.
Okay. I'll just go ahead.
Yeah, sorry. I do have a question. My name is Vishal. I think I did do like but my question is kind of like how, maybe this will kind of lead up to what you're talking about right now, but how would you write something that basically that kind of interfaces between a current classical computing and a quantum computer? So part of it could be working with like a deterministic classical model, and then kind of interfacing with something like using a C++ or Python or Java or something as your classical engine, but then you are feeding the data or streaming the data to some other hardware or some other circuitry that actually uses more of a quantum technology.
Well, you really kind of outlined one of the holy grails of quantum, finding a method to just state your problem in pseudocode or whatever your favorite language is, and then have some sort of technology that can read that code and automatically pull out the parts that are going to do well in the quantum world. And everybody understands that the quantum computing isn't for everything. It does certain algorithms really, really well. The quantum advantage is tied to this, to this concept of the speed up based on entanglement. And but that doesn't mean a quantum computer can do basic accounting. You wouldn't write an accounting package that only ran on quantum computers for your business. So there's a number of things that that are going on there. One technique is to build a machine learning stack that reads code and figures out which pieces can be extracted and sent to the quantum. Beyond that, I don't know. I know that there's probably people out there working on that very same thing. A second part of that is if you study the quantum programming at the gate level, like programming IBM qubits, and start looking at some of the algorithms that are known out there, quantum computing algorithms. A lot of the times you'll run into an explanation where in the explanation, they'll just draw a big box. They'll call it a quantum oracle. They'll tell you what that oracle does, but they make no attempt to figure out how you would actually implement the oracle. So another place where this business of being able to read just generic code and turn it into a quantum oracle is another area that I have some interest in. And again, it's a bit of a holy grail. So somehow you have to read in a program and figure out how to get your quantum, figure out what the quantum steps are to implement that algorithm. So did that answer your question?
Maybe partially. Maybe what you're saying is right now, it's kind of like how maybe during the 90s and 80s, a lot of the compilers were kind of very stupid, but as they proceeded and, a lot of advancements on how to optimize code with the compiler came in, that came in and gave us the framework. If we're going to kind of do this with quantum computing, create a bridge between that, the optimization might come with learning from the compilers. But right now you're saying that, people don't have anything that's really more concrete other than that. It's just kind of a way too new of a field, correct?
Like I said, I believe people are working on that. When you bring optimization into it, optimization is actually a gray area in quantum because it's spread over every step. As we go forward in my presentation, we'll talk about that a little bit. But optimization sometimes is directed at the platform that you're going to deploy to. Sometimes it's directed at your algorithm. But just the ability to solve a problem in a generic language like Python or whatever you choose, and have a program that will read that script and figure out what parts of it can be optimized on a quantum computer, and the next part of that would be to generate the quantum computing code for that. That's a major topic. So hopefully I answered your questions. If there are any more.
Yeah, I can see a few more questions on our chat. So Kayanush is asking about the Julia programming language. So what about Julia? So using Julia instead of Python?
Well, I don't know Julia that much. And if you go back to my slide where there's hundreds of languages, it's like you got to choose the ones you need to learn. Python is at the core of scientific computing. It's at the core of machine learning. It's become the core of frameworks for quantum. So I can't speak to Julia. I don't know what would the benefit of switching to Julia be. That'd be a great question to answer.
All right. maybe I can tell that I've heard that Julia might be quite good for at least simulating a quantum computer, so preparing simulation of quantum computers, because there's quite good advanced and efficient parallelization of computations. So there are already some quantum computing libraries based on Julia as well, but we'll see what the future will bring. As for now, it looks that there are still more Python libraries, and Python is also still getting better and better. So anyway, it looks that the future will be exciting. There's another question from Yunsheng Liu. This is a question about Classic. So Classic is also a platform for developing quantum algorithms. So Yunsheng has asked, is Classic doing similar thing as an analyzer or optimizer in compiler? So Ron, I'm not sure if you are familiar with Classic framework.
That Classic, is that what you're talking about? The quantum language. I haven't studied that in too much depth, but to try to answer the question, yeah, we are stuck with compiler technology as we know it. There may be an opportunity to enhance compiler technology to support languages like Classic. I just don't know what they would be at this point.
Okay, good. Yeah, there was also a follow-up comment from Emil here on chat about Julia, and there was a link to a library called YAO.jl. So it's a quite popular Julia library. There's another question from Martina. Is there any form of quantum Bitcoin? Wow. Sorry if the question is irrelevant.
I'm going to take a pass on that.
Okay, good. All right. And what else? There's another question from Cayetano. Could you comment on quantum parallel computing, MPI, performance, and scaling? So like number of cores in classical computing.
My only comment would be, again, the reason to move to quantum hardware, quantum algorithms, is to take advantage of the quantum, enhancement or the quantum ability to do multiple operations in a single instruction. So it's, they call it the quantum advantage. And it's tied to the concept of entanglement and the ability in superposition. I should have said that before. Superposition and entanglement allows you to set up a quantum register in a state where information can be pulled out of it with just one instruction that it gives you probabilities on what the answer would be. So as far as parallelism in quantum computers, we're still struggling with quantum networks. It isn't clear to me we have a way for a quantum computer at location A to share a qubit with quantum computer at location B, aside from teleportation, which will teleport state information, but is it really teleporting? Is it really sharing the qubit? I don't think the networking has gone beyond anything more than quantum information sharing. So I don't know if that was the basis of the parallel comment or not.
All right, good, thanks. So Helen has posted some comments from YouTube, from Dr. Dirks.
Okay.
But I think that there are other comments and not questions to you, Ron. So Helen, what do you think? I think we can proceed.
Yes, we can proceed.
Okay. Yeah, so let's go.
All right, so I got the slide up for quantum computing now. Let's move on and look at a slice. This is obviously not the entire picture of quantum computing. But here's a list of frameworks. And as I just said, it's not comprehensive. It's just represents offerings that I have run across or that I have looked at. There's certainly many more. Frameworks are typically implemented in a popular classical computer language. And again, the dominant one is Python. And dominant ones are shown in the upper left corner there. You get Python, C#, JavaScript, and Java. The majority of the frameworks listed here are written in Python. Strange is written in Java. And a thing that I ran across called QC Engine is written in JavaScript. Going past frameworks, there are quantum-specific languages. Again, this is probably not a complete list. I'm sure it's not a complete list. QSM and Open and QSM are lower-level gate-based languages that fill the role of assembly language in classical computing. And these languages are very close to the hardware. The other entities listed here claim to be high-level quantum languages, and each one sets out to solve different quantum computing issues and provide unique features. Some of the issues and features include detecting unintentional entanglement, simultaneous support for quantum and classical data types, and detecting redundant gates. The future might see emerging of some of these high-level languages into a single master language, but this is in conflict with competition. So we're going to now just take a quick tour of tool chains. So we're at the main topic of this presentation of what a quantum computing tool chain looks like. A tool chain encompasses all the component tools that are necessary to perform a development cycle and a product life cycle. A tool chain for quantum computing may include some extra steps to deal with the quantum specific issues. First, you're going to need to state the problem, and more, you need to document the problem. Then the more you document the problem, the better off you'll be. Next, quantum will require some algorithm evolution, and you may be doing this in the quantum computing realm and in the classical realm, because let's face it, we're still very much in a hybrid environment these days. Once you get your algorithms worked out and some understanding underway of what you need to do, then you need to capture that understanding in code. Finally, it's time to deploy. Now we'll go into a bit more detail on each of these steps. Statement of the problem. Creating a statement of your problem is probably the most ambiguous step in this development process, as there is no magic recipe. Presented here are a few steps that will contribute to a completed statement. First, classify the problem. Listed here are some common classes, but new classes may emerge from quantum computing. Optimization problems are very common in the quantum world. Next, you want to define the complexity of your problem. This is a major topic in computer science, and we can't do it justice here, so go see your college courses for this. The main thing to understand is which part of the problem will be better served by quantum and which only need classical solution. Beyond these steps, your environment may require other specific steps. The final step is to document everything and use whatever engineering tools that are out there, like graphs, charts, and maps. Now that you have your problem defined, it's time to select or develop the necessary algorithms for your implementation. Given that we are still in the early days of quantum computing and quantum algorithms are evolving as we speak, there is a good chance that you will need to do some algorithm development. Doing algorithm development to research involves a number of topics. The few that are listed here may be tied to your tool chain. First, you need to do the math. If you have done any study of quantum computing, you've undoubtedly been presented with tons of math. Some of the most common math topics for quantum computing are listed here. The good news about math today is that there are a lot of tools available that can help you do the math at very high levels. Tools like GeoGebra, R, and many others also have visualization capabilities and complex equation solvers. There are also numerous math libraries like NumPy that enable you to play with the math, especially in quantum, which is full of matrices, NumPy and its related frameworks are great for that. You know, engineering tools will allow you to capture your algorithm, research and development steps. A simple editor can be used to capture pseudocode and UML directives. Other tools will allow you to graphically capture things like, again, graphs, flowcharts, and state machines. At some point, you might want to simulate and visualize your algorithms. For quantum computing, being able to simulate a quantum algorithm and visualize the state of the entire quantum register at any point in the timeline is very helpful for algorithm development. Simulators for quantum computing are numerous, as each quantum computing language or framework that we have listed in the presentation has access to at least one simulator. Some of them have access to multiple simulators. Although simulators tend to work in the background, as in pay no attention to the person behind that curtain, they output raw data, either at checkpoints or upon completion. This data is great input to visualization tools. So now what I'm going to do, I want to demonstrate a few visualization tools, starting with one that I wrote. And pull this on here. So this tool demonstrates a method for visualizing the inside of a 3D solid object. And the reason I think this is important is because quantum is full of multidimensional problems. So having the ability to build tools that allow you to bring those to life, so to speak, and show them on a two-dimensional screen, I think will be pretty critical. Now, in the case of this thing, what I'm actually doing here is slicing through a solid three-dimensional color cube. And you can see as the slices move through, you can see what colors are at those points in the slice.
Ron, your slide didn't advance. We're still looking at the previous slide.
You're on the do the math?
We're on quantum computing tool chains. What will the future bring? At least that's what I see.
Nobody's seeing the window that I pulled a window onto the presentation?
We are saying do the math, Ron.
Yeah.
Yeah,
So
yeah.
we can see only the slide, so I believe that you should probably start sharing the window.
Okay, I'll have to do it that way. So you guys probably missed the Lex and the Yak slide. Okay, let's do that. And I want this one. I thought this used to work. I could pull it onto the screen that's being shared.
Yes, I
We
think
see
we
it
can
now?
see it. Yes.
Okay. So again, this is a three-dimensional look inside of a solid object, which is a a pretty interesting visualization problem. And again, we have sliders here that basically push this thing through the center so you can see what's inside the cube. Okay. And again, I'll say that this is really important. Like in quantum, has lots of higher dimensional problems, and finding ways to visualize it, I think, will greatly help the understanding of many quantum topics. Okay, so I'll stop this one and get rid of that one. And then I move on to the next one. And where is it? I gotta find it now. So now, are you guys seeing this thing of the block sphere?
Yes.
Okay. So I did a search for a better block sphere. I've noticed that some of the classical ones leave a little bit to desire, but I found this one to be a really nice implementation and visualization. And you can see you can manipulate it here. What I really like about this version is that you can tell precisely which side of the sphere the state vector is pointing to. the side facing you or the back side. I've noticed with some other block sphere implementations, it's not always that easy to figure out. A drawback to the block sphere is that it only shows the state of one qubit. Although, having said that, I guess you could draw more than one vector in here, but it would be an exercise to see whether that provides enough information to give you the whole state of the machine or not.
Well, Ron, it wouldn't if the qubits were entangled.
Exactly. Yeah. And so again, that kind of, keeps this at a visualization of one qubit. Okay, I'll stop this guy. Okay, so now I'm going to show you an example of circle notation, and this is from the O'Reilly book, Programming Quantum Computers by Eric Johnson, Nick Harrigan, Mercedes Gimeno, Segovia. Let me find that one. And so you guys are seeing this O'Reilly page.
Yes.
And this is what was referred to as circle notation. And I've come to learn that there's more than one type of circle notation. This particular one uses a line drawn from the center to the outside to show a rotational vector. And then the blue shading goes from a pinpoint to a full circle to show you a probability index. I have found that this, for some algorithms, depending on how you organize these circles, it can really help understand a lot better, understand the algorithm you're trying to discover a lot better. Let's stop that off. Okay, let me put this back on. I don't know why that stopped working. That was working before. Flying windows on.
It says back on. We're good.
Yeah, but you're not. When I fly a window onto their screen, you're not seeing it, right?
We are only seeing the do the math engineering tools similar to visualize.
Yeah, this was working before. They said it was working. Yeah. Final note on visualization comes from the book Quantum Computing in Action by Johann Voss. And I'm sure some of you will remember that Johann presented Java examples from his book to this group a few months ago. A visualization technique that he uses in this book is to show quantum information about a collection of qubits. Just think of rectangles with shading instead of circles with shading, and the rectangles are organized as a vertical bar. The nice thing about this technique is that the vertical bars can be easily dropped right onto your quantum circuit schematic, allowing you to see the state of the whole system at every step simultaneously. I didn't have a chance to get a graphic for that, but if you have looked at Johann's book in the middle to later chapters, you'll see numerous examples of that. Okay. So the next thing you need to do is capture your understanding in code. You've done the research, you selected and developed all the algorithms your solution will need. Now it's time to capture your research and your understanding. And that's important. It's not just capturing the code, you want to capture your research. This is where quantum computing can utilize many of the same tools used in classical software development environments. Specifically for text or source code, there are many, many options that include everything from your favorite text editor, yay VI, to Jupyter notebooks and others. And people that are doing quantum might find Jupyter notebooks everywhere they look. There are great opportunities for graphical tools to capture quantum computing code. One example is a schematic capture-like tool to draw QC circuits or timelines. And one of the famous ones, which I'm going to share here, is for those of you who have set up an account at IBM and dropped into the IBM Quantum Experience, you might find this pretty familiar. So are we showing the quantum or the IBM Quantum Composer?
Yes.
Okay. So I'm not going to go into this in too much depth, but just to show that you can drag gates out of here and it writes the code for you. You also have some visualization stuff here in the lower center, and you've got some other information about the probabilities of your about the running status of your thing. Here it's selected the probabilities. There's also state vectors that you can put on there. And as later on in the demo, we'll talk a little bit more about IDEs. This is also could be considered an IDE. You can pretty much do everything you need to do inside of this world. It's probably not suited for really large quantum programs, but it's a great place to play. And here again, you'll see there's an over here in this column, popped it right below here, is a different form of the circle notation where the blue shading looks like water filling a fish tank or something. In that, so that's information that's presented differently. Okay, so there's one other IDE that we can take a quick look at. And stop the share. Where's this thing? Yeah. This IDE is again from that O'Reilly book that I mentioned. And you should see Programming Quantum Computers page here. And I highly recommend this book. I got a lot of quantum algorithm understanding out of it. And this is a function, kind of a functional IDE. This is based on the QC engine. I've noticed they recently, well, now it's not there. But this is quantum programming from a JavaScript perspective. This is JavaScript over here. Once again, you have some visualization tools. Over here, you have a schematic, but this is a output only. This, as far as I can tell, it doesn't allow you to edit it, but it just shows you a schematic representation of what your quantum algorithm is doing. Here you have their circle notation. And again, so the nice thing about this is you can get this to organize like in a two-dimensional structure. I found this really beneficial when I was looking at algorithms, quantum algorithms for doing image processing. You could almost sort of see the image based on the shading of these circles. At the very least, you can see what's happening to the state of the full quantum machine a little bit better in 2 dimensions. So, okay. You can be sure that there are many more IDs, some for specific hardware, and I'm sure as time goes on, people will continue to make more of them. Stop that, and let's move. Okay, I'll get this back up. Okay, so the next thing to step into is you've done all your work and it's time to deploy. You need to get this out there in the world. Now this is really forward looking. There's not too many places where algorithms are being deployed into production. I mean, there's a lot of work going on at the different hardware vendors and stuff where people are getting work done, but whether they actually have a deployment step or not is probably arguable. But eventually, deployment is going to become an issue. So moving on now, you've written your code, you've done all the work that is required for the final product, and it's time to deploy. Shown here are steps in the deployment process. And once again, there are many more steps depending on the environment you are working in. I will say that in the quantum computing world, the boundaries between these steps can be quite blurred.
Ron, I
ahead.
think we're seeing what you intend.
What are you seeing?
Anna, would you like to ask a question? Or maybe that was just a mistake.
Yeah, I don't think we were seeing what you intended to show us.
Up in here. What are you seeing now?
Quantum computing tool chains, deploy, compile, optimize, run.
We're on the
Open
one.
discussion.
We're on the deploy one.
Yes.
Quantum computing tool
Saying
chains.
open
deploy.
discussion. I'm saying open discussion, Ron. So I think it could be a local problem.
Yeah.
Which screen are you sharing, Ron?
I am sharing quantum computing tool chains deploy.
Yes, I can see it. Exactly this slide.
Then somewhere there is a
Okay.
problem. It could be local.
Okay. Is everybody seeing this one or just a few people not seeing it?
Now
seeing-
your screen's moving.
Yes,
It's moving.
I see it.
Yep.
Okay. Okay, where was I? Okay, I was saying that in the quantum world, the boundaries between these steps, compile, optimize, run, everybody's seeing that?
Yes, I
Okay.
can see that.
Might be quite blurred. You may not even be able to predict what order to take these steps in. But given that you are at the deployment stage, you might want to try to take a cue from the classical world and employ automation for deployment any place you can. This is effectively quantum DevOps, or let's just call it QDevOps. Did I just coin that as a term? Anybody hear that before? For deployment, you might need to take different steps to compile your product. That's why we have a compile step in the deployment. Maybe the hardware you are deploying to is different from that of your R&D phase. Even if the hardware is the same, production might require more capacity. Production might require different optimization layers or noise mitigation layers. Production might require extra layers to physically get your program to load on a specific device. Installation-specific topology differences may require appropriate compiler options or layers to recognize to reorganize gate instructions. Optimization is listed here as a step, but really in the QC world, optimization is happening at many levels. Some of the items that we are just listed in the compiler step might also be considered optimization tasks. We've seen that many quantum computing domain-specific languages also incorporate optimization features, like was previously mentioned, the unintended entanglement detection and redundant gate removal. Assuming that you have encapsulated your compiling and optimization issues for deployment into a script of some time, it's time to run the script. In today's environment, the run script may need to interact with simulators, quantum hardware, and classical hardware. Yes, I said simulators. There are people out there doing work where they're doing part of the quantum work on a quantum simulator. If the size of the quantum algorithm will fit on one, why not do it over there? In any case, this connectivity of multiple different domains are more reasons to script it. I'm going on to the next slide. Oh, somebody drew on this one. What the heck?
Okay, let's try to remove it.
How did that even happen?
It is possible in Zoom, but
Oh, it is.
yeah. So
You have to disable annotation. Okay. Okay, so now that we've had an overview of what quantum toolchains might look like, we can list a few and take a look at least one. Qiskit is the name of a quantum. Qiskit is the name of a number of quantum things in IBM land, and it's pretty expansive. I was not able to find a single graphic that maps out all of the components into something that looks like a tool chain. There are tons of graphics in Qiskit, and this is just related to how much stuff is over there. Qiskit has been very IBM slanted, but I recently noticed that they are now starting to list back-end products for other quantum hardware like trapped ions. Last January 14th, 2023, Catherine Spendier presented TCAT by Quantinium to this group. If you didn't see that presentation, I highly recommend a visit to the recording, and you can contact the Washington DC Quantum Group to find where that's been uploaded, I believe, on YouTube. Okay, so let's gonna take a quick look at TCAT. I pronounced it wrong the first time, didn't I? So now you should be seeing a slide. This is from Catherine's presentation, and she graciously allowed me to include it with permission. So I was very happy that she did that. This graphic on this slide nicely shows the partitions of a tool chain. Input on the left, intermediate processing in the middle, and deployment on the right. Clearly, there are more. Now, this gives you a great understanding of the organization on what's going on at TCAT. I wish there was something more like this, like for some of the other tool chains that are out there. There may be for tool chains that I haven't looked at yet. So,
excuse me, just wanted to have a quick question. Can you bypass the Python API and go into the TCAT's compiler specifically?
That would be a question you want to send off to Quantinium. I do remember asking Catherine during her presentation that it seemed like it's possible just start your algorithm in PyTicket. And she didn't seem to have any reason why you couldn't do that. It appears that you can take these. On the left, you have these quantum computing languages that can be imported into Ticket. And although I didn't get a specific answering, but I believe what they do is they translate it to the PyTicket, which is where, and then after that, you have the compilers with the optimization steps. And then after that, you have the tools to deploy it to specific hardware. So did I answer your question?
I think you didn't. I was just kind of saying, like, instead of going to the P-ticket, actually just use the ticket compiler because it's a C++ library, and kind of bypass that if you're looking for performance and optimization.
I'm going to guess. I'm going to guess yes, because they were very deliberate at showing this graphic in layers. So the important thing you would need to know is what does the ticket compiler need for input. So if you can provide that input, you should be able to run the compiler standalone, I would guess. That's just a guess, though.
Yeah, thank you.
Okay, I will stop there.
Just maybe as a follow-up question, but is right now is like the simulator hardware considered similar to a debugger in classical computing?
A classical simulator? Is that?
No, I was saying like the hardware and simulator step, the last portion, is that kind of similar to what you would have as a debugger? If you're writing code in like any language, usually you want to have a debugger to see and verify that your code is running as you would normally have in like any language. It's doing it what you expect it to do, or you need to make some changes so that it may need to cover over edge cases, or maybe it's not doing exactly what you want it to do, so you might need to rework your code.
Okay. Again, another question you might want to direct at people at Quantinuum. The point of this graphic for my presentation is to show a complete tool chain that is out there for the quantum world. So I have full intention into learning Ticket, but I can't answer that specific question for that back-end phase right now.
Okay, thank you.
Okay, stop that. Okay, should be back to sharing quantum computing now, quantum tool chains.
Yes.
So, okay. And we'll move on to the next slide. Okay, so before I go into the future stuff, if there are any other questions, we can clear those now.
Okay, there are some discussions and links that are posted on our chat, but I don't think there are some questions there. So maybe there are questions you can unmute and ask. Yes, Vishal?
Sure.
Yeah, so I was kind of wondering, I think a lot of this looks like it's dealing with graphical and kind of visual thing, but I think if you're looking like kind of conventional programmer, you might want to kind of have any text and kind of text editor. Is that actually is there something that can kind of put everything into maybe a text format, so like when you're doing this in a live session, you can kind of see the text for people who have more experience with the programming side, rather than kind of like a newbie programmer. And then kind of another question, maybe kind of if you wanted to see like some languages for quantum computing, is there anything on Godbolt to kind of do an experimentation, or do you need these other kind of IDEs and other interfaces to do that?
To address the first part of your first question, one of the beauties, the nice things about the quantum world and existing quantum computing languages is there's no reason you can't use classical text editors and IDEs that are out there. In fact, that's what most of the people do. And like I listed on the previous slide, Jupyter Notebook, it's used all over machine learning land, and it's just a standard tool. Lots of quantum computing gets done just inside of a Jupyter Notebook. There's no reason, a lot of these languages are text-based, so there's no reason you can't use the IDE, your favorite IDE of choice. So I know that there's, it's just a matter of, do you have a plugin for that IDE for a specific language? So there's that. So I don't know that there's any reason to get too excited about future text IDEs for quantum. They're pretty much state of the art at this point, but if there's an idea about what could be improved there, that would be great. I think the future for front end capture would be more for graphical based ways of writing the code, and we'll get into that in a little bit here. And could you repeat your second question again?
Yes. So the issue is that if you wanted to look at like writing a quantum hardware, do you have to use kind of like these on site, or is there any sort of thing that you can go through and look at how your quantum code would translate into the underlying hardware code using Godbolt?
Okay, I'm not familiar with what Godbolt is, so I don't think I can answer that.
It's basically, it's also called Compiler Explorer. Basically, you write your code in the language and it translates that into the underlying operating or underlying source code.
Okay, the only thing I can pull out of that is lots of these environments have simulators, software simulators that are built in where you can run your quantum algorithms, assuming that they're small enough to fit inside the simulator. I don't really know how to address Godbolt or anything like that. Okay.
Thank you.
Okay, so we do have the future slide up, everybody.
We do.
Okay.
Yes.
So I'm sorry that I just wondered, because I know you, I follow you.
I'm having trouble hearing you.
Yeah. Sorry, so I may ask that already was asked, but I know you're doing with Anna a lot of new solutions, and they probably are emergent of some pending issues, trying to solve those. So what are those pending issues that around compilers? Some of the previous questions, last question.
Can we save that for the open discussion?
Absolutely.
Okay. So I'm going to get through this and then we're almost done. So what is the future going to look like? Here is just a short list of areas I believe enhancements could be made. There are tools out there that use interactive graphical building techniques like what we saw in the IBM Explorer suite, but could they be better? I'm going to go ahead and show an application that I put together that uses a graphical code building interface based on blocks. So once again, I got to do a stop share and a reshare. Where did you pick this window? So you should be seeing a window that says AG Code Builder on it.
Yeah, we can see it.
Okay. So this AG Code Builder is something I built a while ago that was a proof of concept, and it's based on a blocks framework. If you're familiar with the language Snap or Scratch, you'll probably recognize what's going on here. You can see that we've got things we can build code from. They're blocks and they're stored in a hierarchy over here. And I've dragged some out and I can very quickly, I can duplicate them, make a couple copies here. I can snap them together. I can change this one to an X gate. I can change this one to a different qubit. I can say how many I want it to be, snap them together, keep going here. And eventually you got to do a measurement, right? Okay, so I just built a quantum circuit. Unfortunately, there's no brains behind these blocks to actually implement a quantum circuit. The point is this is a graphical way of building stuff. And I'm not going to pretend that this is a quantum tool, but I hope, like I said, you can see it has possibilities. These block-based languages were designed for children to teach them how to program. And to that end, you'll notice that the blocks have different connectors, more like puzzle pieces. You'll see that here, right? It kind of looks like a puzzle piece. The connectors can be configured such that blocks can only be snapped together if it is legal to do so. And by legal, I mean syntactically, grammatically correct for the language. In this way, blocks that are connected together are syntactically safe, and a whole collection of correctly connected blocks automatically form an abstract syntax tree. So that's a whole step you can just get for free. Children using these blocks don't need to learn syntax or AST concept, at least not right away. Basically, this type of technology at a much higher level, where you're snapping together algorithm blocks and not just quantum circuit, might be something that will help the future build legal quantum circuits, algorithms, and programs. Okay, and we move on. Let's see, I think I'm done with that. So we'll put that one away. Okay, we should be back to the future slide.
Yes.
Okay. Okay. So in computer-aided design world, new input hardware was developed that helped designers manipulate 3D objects in multiple axes or dimensions at the same time. If anybody knows anything about CAD/CAM software, and ever saw somebody use what's an input device called a space ball, I think you'll know what I'm talking about. With something like a new input device like a space ball, would that be something that would be of help in the QC world? Along those same lines, will virtual reality or augmented reality bring new capabilities to quantum computing? Holographic projections just got to have some kind of connection, right? Holographs, quantum mechanics. Okay. Well, the future, and then the last thing I have here for the future is consolidation. Will the future consolidate quantum computing technology? And I have the comment, how many quantum computing languages do we really need? I have hope that there will be a convergence of these languages into, a couple that are mainstream and basically do everything you need it to do. But based on the classical world and the hundreds of languages that are out there, I don't really have that much hope. And plus, this consolidation, as I think I stated before, goes against competition. But it'd be nice if there was less learning curves to climb in just having to deal with quantum algorithms directly.
That's also true for almost anything else out there, especially
Exactly.
in the computer world. I mean, it's kind of, you can't just be inundated by the rapid change in technology. I mean, I was a C++ programmer, and I swear I don't know enough C++, yet I'm a Java programmer, and now it seems like Python is the next thing.
But
Yeah,
I think that sorry, I was going to put this towards a discussion, but I was saying, like, I think a consolidation may not be kind of like the whole point, but like at least having a common framework might be better. So if we can have instead of just like a pure language consolidation, we could have kind of a couple of hundreds of languages, but kind of have the same type of structure, like how C is kind of the default structure of most current programming languages, but you're not all of the code that you write in C is actually going to be valid as Java code or as C++ code or as Python code or etc. You do have some certain rules, but as long as you know kind of the basic syntax, you can go from one language to another.
Well, the devil is in the detail. I mean,
right.
For anyone who learned, C++, Java, and C# and F#, and there have been people out there who tried. I know Microsoft put out like a translation app that would help.
Okay, just interrupt real quick. So this concludes my presentation. Okay. I want to thank the Washington, D.C. Quantum Group, and specifically Helen, for making this happen. And to all the attendees, thank you for coming. I really appreciate everyone's support. So now I'm very happy to open the floor for questions and discussions, and would love to hear ideas or concepts about future quantum computing tools. So now, open discussion.
Yeah, I think yeah, that's what we were discussing is like when you were um, mentioning like you wanted to kind of consolidate rather than consolidate for just only like having a few languages, basically having kind of a structure for different languages. So you kind of when you learn like one language, you can learn um, other quantum computing tools and languages, uh, and kind of jump from there with minimal things. Maybe you might need to know a little bit more of the details of what the capabilities of the language are, but you can jump from one language to another language rather easily, rather than just trying to learn one syntax and then you have to learn another syntax for that I think is basically kind of the consolidation that you would want, just kind of a open framework that almost anyone can go for learning one quantum computing language versus another. Am I correct or am I incorrect?
Well, as a software developer, writing the program takes up maybe 10% of your time.
Right.
The other 80% of your time is spent in debugging it and
Yeah.
making it do exactly what you want. A lot of marketing people, come in there and they have an idea and you start coding it up, and then you really learn that, well, that's a good idea, but it's not really the way you want to do it. And it takes a lot of hands-on learning. And even with, man, I've been spending 2 weeks on fixing some stupid bugs in my program. And it's like my boss, why is it taking you so long? Well, geez, sir, I'm just not as smart as you are.
Yeah.
I think a lot of that. I'm sorry, go ahead.
I'd like to make a comment about the language C. The C lexicon, which is the first step in the compiler, is actually the same lexicon used for a number of languages. Early versions of JavaScript and Java, for example, basically they didn't even write their own lexer. They just used the C lexicon, and you can see that the similarity between C and Java and JavaScript, where those things pop up. Current versions of that probably have diverted a little bit, but the point of that is why reinvent the wheel? In the quantum computer arena, you have lots of math to do. Why build all these math modules if you can just write something in Python, pull in NumPy, manipulate matrices and arrays? It just makes a lot of sense to leverage what's out there. In the long run, if there's a convergence on specific quantum languages, I think they will be implemented in backends that hide a lot of that stuff from the end user. So hopefully that's the direction things are going in.
I do have one more question that I would like to ask. Maybe it's something that's not really explained in detail, and maybe it may be beyond the scope of the presentation. But I noticed that you were talking about QML and OpenQML. Is there any like current compilers that actually or tool chains that you could use to translate current code to QML or OpenQML? I'll mute myself.
In terms of QML, you're talking about quantum machine learning?
No, I think like sorry, not QML. I was thinking I think it's QAS, the assembly quantum assembly language.
Okay, what about it?
So basically, I was wondering, is there any like compiler tool chain that can take in like current code and translate that into or target the quantum assembly language?
Well, it's funny you mentioned that. That is a project that I've been looking into doing. There's a number of quantum computing languages out there that don't have any back end whatsoever. So I've been researching the possibility of writing a compiler for these languages, and I think the choice was to have it, read in one of these specific quantum computing specific languages and output QSM.
Well, my thing was I was actually saying like writing in like C or C++ and then just targeting like using the compiler switch to target the QSM
Yeah,
using.
we talked about that a little bit. Again, it's a bit of the holy grail. You need a big step in between reading a generic algorithm written in C or Python or whatever your favorite language is, and pulling out the sections that would have figuring out where in that program you can make use of the quantum advantage. It makes no sense to me to translate an entire algorithm to quantum at this point. Which you're going to need to be able to do is figure out what parts of it will benefit from the quantum advantage. Things like optimization, eigenvalue finders, things like that. So anybody have any out of the box ideas about future tools when it comes to writing?
Can I ask you some questions? Simple one.
Sure.
Yeah, my name is Gaetano. Thanks very much, Ron, for your very enlightening presentation. I did enjoy your presentation. I work in the engineering field, and I just wonder, currently some of the engineering problem, like in fluid dynamics, like weather forecast, things like that, some of these physical phenomena takes a long time to simulate. A few seconds of simulation could take several weeks in classical computer using hundreds and hundreds of cores.
Yeah.
So I just wonder what quantum computer could bring to us.
Well, the classical joke for that, and you're talking about computational fluid dynamics or finite element analysis, and the standard engineering joke for that is we can absolutely predict tomorrow's weather to 100% accuracy. It just takes us 3 weeks to do it. What? No drum shot? What? No, sorry. I'm aware of it. One program or one group that is using quantum to enhance quantum fluid dynamics calculations. It appears, I believe they're using the D-Wave system, and at the time I saw that presentation, they were getting somewhere in the neighborhood of a 4 to 5, 6% improvement. So you need if that 4 or 5 or 6% improvement is worth the budget, that's sort of where we were at least a few months ago. I haven't been able to keep track of what they've been doing since then.
Yeah, thank you.
Do you see any? Oh, I'm sorry. I was going to say, do you see any use of GPUs in this?
I'm sorry.
Anne has raised her hand, so Anne, maybe you can ask a question.
Sure, thank you. Great presentation. I just want to go on a little bit about Ron, when you just mentioned some of the use cases. If somebody's sort of in more of a management than a technical position, and they have some business model, whatever they do, it sounds like quantum computing, all the hype we hear is it's like it's going to change the world. I guess every new blockchain was going to change the world, but in point of fact, it's another back-end tool, as you said, which will be built into an overall tech stack, it sounds like, to optimize certain things, certain functionalities. For example, I heard a guy a couple years ago from NIST talking about how it could increased, as I understood it, the granularity of global GPS synchronization. We'll get even finer and finer divisions of time, so to speak, and that it within shorter periods of time rather than 3 weeks to predict the weather 100% the next day. Is that kind of a correct read from a non-technical person? In other words, this isn't like going online. In the 1990s, businesses really weren't ready for the idea of the sudden and ubiquitous impact that the internet would have, with online websites, online businesses, social media, et cetera, et cetera. I'm getting the impression that that is not what quantum computing is, that it's a back end optimizer of something, of some compute functionality. Any reaction to that, or is that just too stupid to respond to? Which I wouldn't be surprised.
You're not incorrect. There's a lot of quantum hype. I mean, quantum has become the go-to buzzword. Like back in the day when everything was better if you added an LED to it. I'm confident that as quantum hardware gets better, and I'm pretty confident it will get better, and we start getting out of the NIST era and have devices that are more practical to operate, practical to own, practical to have, that more and more algorithms will come online. I mean, there are algorithms that I know of that people are making headway with and getting results. And as I said, if you're getting a 5 or 6% improvement by using the quantum advantage, it better be in an environment where that investment is worth that 5 or 6%. But yeah, there's a lot of hype going on out there. There's a lot of people claiming that it'll rejuvenate, reorganize the world. Maybe so, but I'm also pretty confident that we won't be replacing classical computers. I think I stated earlier that I see no point in building an accounting system out of quantum computers. Quantum computers have a major difficulty just doing math, simple arithmetic. That's not what they're going to be good at. They're going to be good at solving problems that can be expressed in a quantum matrix or register, and then an quantum algorithm is run on that to get the answer for all the possibilities simultaneously. But that limits you to what is going to be useful.
Great, thank you.
Appreciate it.
Sorry, but this is something that I was kind of thinking a little bit more, but for you were mentioning, I think a little bit earlier during the talk about teleportation, could there be like a quantum circuit where you're dealing with teleportation for messages that you have on a kind of a server, in one location where you're trying to listen to the kind of the, get the current state of the information, or this thing processes on the server in nearly real time, or without having to have stuff co-located at the same site. So you're just using the like a quantum communication between two servers that are separated by a significant distance. Is that something that would be part of the quantum computing realm?
Well, there are lots of people working on quantum networking, and if my friend Anna is still in the room, she would be the one to ask about quantum teleportation. She's a straight up expert on that. My understanding of it is it's still difficult to make happen, although people are using it or variations of it to do things like quantum key exchange, which are in comparison to classical networks, are tiny bits of data packets that they are exchanging. And for the near future, quantum networks might only be useful for that. This is another area where some people think a quantum network will replace the classical network. I don't see that happening near term. But again, understanding the teleportation, I think if Anna was still here, she could fill in those gaps better than I could.
Right. No, I was just saying, like, I think it is possible. I think like the people who I can see really wanting to invest in this would be kind of like the hedge funds and trading where they're doing high frequency trading. Right now they're trying to keep everything co-located to servers within the same data center to get the lowest latency. But if you do have like some way to have those information packets delivered through a teleportation quantum computing network, I think that probably would be worth it. And I could see like a lot of trading companies trying to go into it, especially since making those trades on that level is actually maybe like hundreds of billions of dollars if you can do it fast.
I think you're merging a whole bunch of topics into one there. I'm aware that there is supposedly a company on the East Coast that is selling quantum key distribution as a service. And here in the Washington, D.C. group, a couple months back, we had a presentation by a gentleman who talked about China's network for distributing keys, and it was using satellites and stuff like that. So as I'm aware of, these networks are doing everything they can just to exchange safe quantum keys. But there are people out there working on it, so we'll see what the future brings in networking.
Hey Ron,
yes.
Where could I read up on this CG code you showed?
I'm sorry?
The CG code you showed, in some CG code that, kind of algorithm development on this. You just showed something, right?
CG code?
Yes, CG code that, kind of puzzle you for the kids.
Oh, the block? Oh, the AG code builder?
AG code, I'm sorry, AG code.
Yeah, that's based on a block framework that's open source that's out there.
Is there any?
Did you have a specific question about it?
I can read up on that. Is there anywhere I can, AG code? More on that?
Well, no, AG code is a thing that I wrote, but it's based on a framework called Blockly. You can go find that. I believe, I don't know if that's a Google thing or it's out there. You can you go out there and download the framework.
Okay, thank you.
Mm-hmm.
All right. Do we have more questions, Ron?
I put 2 in the chat.
What's the chat?
Go
ahead and ask him.
Yeah, so there was a question whether
I can ask.
Yes. So Sonia, please ask. Mm-hmm.
Yeah, so we currently use GPUs for doing computing for math and AI and stuff like that. Do you see the use of that in quantum computing being a possibility, but given the fact that you've got memory limitations, there's a limit to which you can like load that up. So maybe ganging a few of those together will expand it, but there's definitely a limit. But is it worth companies going down that road, or is it like, yeah, forget that, let's just build a simulator that runs with gobs of memory? And
well, I know that NVIDIA is putting a lot of effort into their quantum version of CUDA, which they call QCUDA, or I don't know how they pronounce it. It's CUDA, where they are building libraries to do quantum simulators on their GPUs. You know, the issue with memory is every time you build a quantum algorithm that needs one more quantum bit, every time you add a bit, you have to double the memory you have for simulation. There's some people out there we're talking about, they have simulators that are as wide as 30 to 32 bits. Takes gigabytes, if not more, of core memory if you want the thing to run reasonably fast. But even the issue of, and this is where NVIDIA steps in, if you've got a matrix that is a state matrix that is 8 gigabytes in size, you know, how do you, just the process of doing one quantum step, which involves doing a matrix operation on a 1 gigabyte or an 8 gigabyte size matrix, that's where the GPUs kick in, because they're really good at doing things in parallel and breaking up matrix problems into or breaking them into tensor problems or something like that. So to answer your question, I know NVIDIA is doing a lot of work in that area, but eventually simulators, it'll get to the point where simulators just can't be expanded anymore.
Yeah, that was my sense. Yeah, it's like you can go only so far, and then you hit a brick wall on memory.
Exactly. I mean, and there's people out there talking about algorithms, right? Well, if we only had a quantum computer that had 400 qubits, okay, well, we have no way of simulating 400 qubits. So you got to hope that someday a 400 qubit machine will pop up. And IBM says that they're close, or that they have their Osprey device, which is 432 qubits. But they're fighting the same problems: coherence, noise, and all that stuff. So what you really need is 432 perfect qubits. That doesn't exist yet.
Okay, thanks, Ron. Do we have more questions, Ron?
Yes, there's one more question. Can it be that in the distant future, CPUs will be the special purpose processors in case someone wants to do etc. accounting fast, because the qubit is a generalization of the bits?
I'm sorry, could you repeat that?
The question is on the chat. It looks like the last question. Can it be that in the distant future, CPUs will be the special purpose processors in case someone wants to do, for example, accounting fast, because the qubit is the generalization of the bits?
I'm just reading the.
It's a question from Thomas, but I believe
I just found it. Again, I don't see any purpose in using quantum resources to do accounting. I mean, we have classical digital architecture that can add two numbers together in sub nanoseconds. So how much fast? I mean, quantum computers are not physically faster than classical computers. They get their advantage from the quantum advantage of superposition and entanglement, and the ability to convert an exponential problem into a polynomial problem. So I don't know that makes much sense to.
Hi, Ron. So
I'm not sure I understand the whole question.
Yeah. The question was basically that I can imagine that in the future, producing qubits will be much cheaper, and they will be pretty fast. And then we'll have like the general purpose computer, which will be a quantum computer. And then we can do accounting on it because everything is so cheap. However, it can be that somebody wants to do accounting or any other classical problem very fast, and then they will go to wherever Azure cloud, and they will find a special purpose machine, which is like a classical computer, and then they can do it much faster. However, in the general case, they may not need that speed for accounting, and then they can do it on qubits. And of course, I say distant future because it has to be cheap enough and fast enough.
I would just like to add, I think, Ron, the direction where the question was, like, we have so many small processes which are very, very task centric. And that is possible only because the chip technology and everything has gone so cheap to produce a small purpose-based chip and then produce multiples of that. So where the previous comment was, and the question was that maybe in the distant future when that quantum-based computers will be so cheap, maybe we may be using them for any purpose or special purpose. But that's where you had made a nice comment earlier also in the beginning of your presentation, which goes always true, that you can have a Ferrari, you can have a Toyota Camry. It depends where you want to use what, for what purpose. Because the distance point A to point B, the distance can be covered, but it depends how much cost you want to incur, how fast you want to get there, and is it really feasible to spend that piece on an expensive machine or a cheaper machine? And is this application more centric towards quantum to solve, or it's for any classical computer to help? Well, quantum computers, an example is Chicago computing, where people have tried to put quantum computing to work because of the spectrum set of stocks they have taken into consideration, and they have put and tried to work that as well. But then it depends. Where is your focus? What are you planning to achieve? What is the end purpose, end goal? And accordingly, you can use which purpose. But to answer both sides, yes, it depends. That is the final answer there, that you need to decide where you are headed, what you want to achieve, how much you have, what you have. And as you said, that whenever you are even simulating and the memory requirement goes double, those were the problems 15, 20 years ago with AI and ML technology as well, where we had the algorithms available, we had everything available, but with the recursion algorithms, the moment they will try to recurse, the memory was not available to support, the physical memory was not there to support. As things got cheaper, memory became available, this became reality. And as computers and quantum computers, they will become more cheap. Well, we will have the luxury, but as of now, definitely that luxury is not there. So to go with your comment, yes, distant future may have a totally different thing in store for us. And this is Virendra Galotra, not Vishal. Thank you.
Yeah, I agree with kind of what you're saying. And as far as if at some point in the distant future that quantum computers are that easy to obtain, I mean, as of today, as far as I know, all quantum hardware has incredible elaborate array of support infrastructure. IBM's 432 qubit wafer, which they supposedly are going to bring online any moment now, requires that you run the chip at near absolute zero. Just the amount of refrigeration technology it takes. This is not going to show up on your desktop in the near term. So, but once again, even if you had a perfect quantum computer, and your problem is to do accounting, which is basically to add, subtract numbers.
True.
Are you really going to want to use your quantum computer to do that when the quantum computer could be working on, computational fluid dynamics and doing better weather prediction and
Correct.
in solving chemical problems for making fertilizer or finding drugs. So.
And going back to your joke, Ron,
in the coming future, if they're that prevalent, I mean, you got a whole different domain to look at. So
right.
Before we get to an end, and I'm here to stay for a little while. I just wanted to let everybody know that I'm definitely open to consulting for anybody who wants to work on a compiler, or has any openings for compiler work, or quantum work at an entry level, or quantum machine learning is another area I'm very interested in. So I just wanted to let everybody know that before this wraps up. And again, if you know, I was hoping there would be some ideas about tools that we can think about for the current environment that could be added to the tool chain. So I don't know if anybody had any additional ideas in that area.
Did you mention Classic and the way they're doing things?
Pardon me?
Did you mention the company Classic? I think they're out of Israel. They're doing something
Yes.
along the same lines.
Yeah, I think there was a question about Classic. It's something I need to go look at. When the question first came up, I thought they were talking about classic computing, not the company Class IQ, I think is the way it's spelled. But
Yep, that's
definitely
that's
some place to
correct.
go look.
All right. I remember that people from this Class IQ company had also talked during one of the previous Washington quantum computing meetups. So there should be a recording available on our YouTube channel if you are interested. But yeah, do we have more questions to Ron?
Want to expand on the one?
Itamar, yes.
Yes. You hear me? Do you hear me okay?
Volume.
You hear or you don't?
It's a little better.
Okay. So I'll get closer to the machine.
Oh, that's much better.
And I want to expand on the issues, pending issues that you may have answered by saying you're interested in compilers. And I'm on another level, not so deep, close to machine language as compiler writers are, but I like to know, used to be 20 years ago, people talked about 4-generation language, which says that, hey, I want to go from A to B. I have a data set. I want to do it in Python. I want to perform ABCD tasks. Please write me the code. So I'm like, and my reason is because quantum computing is going to be proliferated and ubiquitous in terms of public interest. Many, many people are interested in that. And those people don't know C++ and would never know, and would never know compilers to the level that you know. So the question is anybody working on that?
If I understand your question, I know there is work being done using machine learning, and you can get, it's my understanding, you can download plugins for various IDEs and for various languages where you basically write in the description for a function, and this machine learning tool will write the function for you. I don't know, is that something that you were referring to specifically? I'm not sure which companies are doing that, but I have seen demonstrations of it.
I would love to know a list of these companies, but my question goes a bit further. Say I used to do Fortran and did my living on Fortran, okay? Now Fortran was formula translation, which means it's very close, in fact, to natural language. I want to go from A to B. And I don't want to know all those systems and all those compilers and caveats. You put a language to Slack about Python, and you get all kinds of labyrinth style answers that don't really answer your problem. So
Sure.
maybe there is room to write something for the spoiled, ignorant, computer science ignorant fellow who wants to do some interesting ideas.
Again, I know there's machine learning tools out there that take input, just raw natural language as a description, like for a function, and it will write it. And somebody put in the chat GPT. I'm not sure if chat GPT can do that, but it's basically the same type of technology. I see that definitely mapping forward into the quantum world, where as quantum algorithms become more understandable and more practical, that these will be able to be added to the training of those machine learning stacks, so that when you put in a problem in just plain natural language, that it will find a solution or build you a solution in whatever language you tell it, whether it be Python or pick your quantum computing language of choice. I definitely see that coming down the line for sure.
Okay, wonderful.
If anybody knows of the plugins for like Visual Studio or some of the other IDEs that give you that ability to, it's like you hit an F key and type in a description, or you basically put the description in your code, like in a comment, highlight it, and then ask this tool to write the code for it. Obviously, I haven't seen. When I saw that presentation a while ago, it was really good for simple functions, but it'll definitely get better as time goes on. So that technology is out there, and if you haven't looked at Chat GPT, it's
Yes,
crazy. It's totally crazy.
totally time changer it is.
Yeah.
It's going to totally change the way you are going to get your search results. And Google has lost sleep for the timing. I'm sure they will come up with some competition, and they are trying to work through DeepMind technology. But we'll see. Next 6 months to 1 year will be very interesting with these two technologies fighting for their space or retaining their space in the search world.
Absolutely.
All right. Do we have more questions?
I saw a question. I wonder how long before ChatGPT can do that.
What?
I think that question was referring to can Chat GPT write Python code, for example. I don't know that it can, but I wouldn't be surprised.
Not just Python, anything really.
Yeah.
Yes,
that was just an example. Yeah. It already can.
Yes.
It is doing some to that extent where people are worried about the negative use of ChatGPT technology. So
yeah,
it's like that's where regulations and everything will be needed, so that people can then really not misuse this technology. But then that's always very challenging when it comes to all these new AI-based technologies, which are going to change the world. And of course, Hawkins, what he said, that we could be bringing our own disaster. That's something which one has to really, really go very careful about. And I remember one student from MIT was already challenging ChatGPT and its availability like that. Some stuff is going on. That's why I said, very interesting time to follow, to see what Microsoft and Google are going to do in the next 1 to 2 years.
So I did ask ChatGPT, to generate some code for doing matrix multiplications, Kronecker ad in particular, and no, it wasn't correct. I had to correct the code. So
it can give you a skeleton. It can give you a max skeleton. That's what I think at the moment. It's not that.
Oh yeah, definitely.
But then you can correct. But that means, again, it's the same story. When cloud technology came into being a few years ago, people were very worried. But yet somebody is needed to run the cloud for you. It may be the number goes less, the jobs orientation and the skills get reoriented. So we make life easier. But obviously, yes, the bad code, you have to fix it. You cannot rely on what exactly is blindly generated by these code generators. And as rich the technology is, the danger and the beauty both lie together in one thing, that how this technology is going to self-learn. That capability is going to make it beautiful, and that is going to make it worse also, dangerous part of it.
It comes down to trust but verify. Always verify.
That's right.
All right. Do we have more questions?
Yes.
Yep.
Hello.
Go on. Yes, go on, Abdullah.
Please, my question is about how to use the quantum technologies, quantum computing technologies, to simulate the more advanced nanoelectronics devices and quantum devices. Just like in TCAD.
How to use quantum technology to simulate quantum devices? Was that your question?
Yes, like using advanced TCAD simulators like nano TCAD in Silvaco and quantum ATK and Centaurus simulator.
Yes, so many of those simulators are classical computers that simulate quantum computers.
Yes,
so they'll have limitations.
Yes, they have limitation. Can we speed up the simulation of these advanced devices using the quantum computing technology?
Well, the idea is to actually use quantum computers instead of the simulator at some point. I'm not really sure where. It's I don't know. Interesting concept though. I don't really know how to answer that. It's if you're using a classical computer to simulate a quantum register, for example, to run a quantum algorithm. If you had a quantum computer that could speed that up,
the hybrid between classical and quantum computing.
Yeah, if you had a quantum computer that could speed up the simulator, why wouldn't you just use the quantum computer?
So the actual quantum computers we can simulate the quantum devices on the actual quantum computer, or it is a bit complicated?
Well, the classical computers that run quantum simulators are doing it at a mathematical level. Actually simulating the devices themselves, there may be some work in that area that's a little outside of what I know about.
Right.
Okay, thank you.
Good.
I did see a question I wanted to, was talking about TPUs versus GPUs. I just wanted to note that NVIDIA's latest GPU chips have a number of what they call tensor processors built into it.
Mm-hmm.
So I don't think you have to choose. I think they're just going to merge together.
All right, good. I can see that George has raised his hand. So George, would you like to ask the next question?
Hello, Ron. Thank you for a lovely, comprehensive overview of the toolchain landscape, especially with the deep dive into languages and compilers. I was interested where in the different layers would the input-output go? You know, getting data in and out of the quantum world. even with GPUs, this is a challenge that your bottleneck isn't the speed of the GPU, but just getting the data in and out. And I was interested where in the tool chain this problem fits in.
I think that's going to eventually wind up being in the deployment step, where if you want to move a quantum solution into production, you're going to have to come up with a way of encoding your input into the quantum registers and then running your quantum algorithm. It's not a trivial step. And there's probably going to have to be a lot more work in that area to get that to happen. I mean, most of the time, if you see a paper or something on a quantum algorithm, they're talking about iterating one pass of the algorithm for one set of input data. They don't spend a lot of time on, well, how would you do this if you had a whole list of data or something like that. But having said that, again, the people that are using things like the D-Wave hardware in exploiting the ability of the D-Wave hardware to do quantum optimization algorithms faster than like the superconducting versions or whatever. You have to look at what sort of improvement they're getting. And again, that's a great question of like how, where is the step to get your data encoded properly so it can be delivered to the input of your quantum algorithm. I don't think it's trivial. I just haven't seen anybody talk too much about that though.
Okay, good. Thanks, Ron. Do we have more questions now?
Well, okay then. Really appreciate all the fine comments and everybody's attention. This is real fun.
Thank you all.
Thank you for
Ron.
coming.
Wonderful.
Yes, thank you.
Thank you, Ron. Thank you, Helen.
Everyone's very welcome.
Thank you, everyone.